This work presents contingency games for multi-agent interaction. Real-world multi-agent interactions, such as the one shown here, pose several challenges for autonomous robots, such as intelligent vehicles. In particular, actions of multiple agents are often interdependent, so that a robot's actions depend not only on its own intent, but also on the intents of other agents, such as nearby pedestrians. However, the exact intents of other agents are often uncertain and may only become clear to the robot later during the interaction. To act safely and efficiently in such scenarios, robots must therefore make their actions contingent on future observations. In this work, we formalize this kind of reasoning by introducing contingency games, a mathematical model for planning contingencies through the lens of dynamic game theory. Contingency games allow a robot to plan with the current uncertainty in their belief, while anticipating certainty at a future time, TB, the so-called branching time. Before the branching time, the robot develops a single plan that considers all hypotheses with costs weighted by their likelihood. After the branching time, the robot reaches certainty and thus generates a separate plan conditioned on each outcome. By solving a contingency game, the robot jointly generates multi-hypothesis predictions of other agents' behavior and a corresponding conditional motion plan for itself. In our paper, we characterize the behavior induced by this interaction model. Varying the belief demonstrates how the robot balances the cost of each hypothesis according to its likelihood. Varying the branching time shows how the robot exploits future information gains to balance safety and efficiency. At the two extremes of the branching time, contingency games include established game-theoretic planning paradigms as a special case, with games that assume no uncertainty at one extreme, and multi-hypothesis games that plan in expectation over fixed uncertainty at the other extreme. By estimating the belief and the branching time online, contingency games provide an adaptive game-theoretic motion planning framework. In our experiments, we compare our interaction model against non-contingent game planners from both extremes of the design spectrum. These comparisons include a certainty-equivalent baseline that considers only the most likely intent of the human at every time step, and a non-contingent multi-hypothesis baseline that ignores future uncertainty reduction. To demonstrate the utility of estimating the branching time online, we further consider three variants of contingency games. One that utilizes a simple heuristic to approximate the branching time from the current belief, one that always chooses the branching time one time step into the future, and one that has access to the true branching time as computed in hindsight. We compare these methods in extensive simulation experiments of two closed-loop interaction scenarios inspired by autonomous driving. In the first scenario, the robot encounters a jaywalking pedestrian with an uncertain goal on either the left or the right of the lane. In the second scenario, the robot seeks to overtake slow traffic with uncertainty about the lane-changing intentions of the vehicle ahead. For both scenarios, we simulate interactions at 70 different initial states for each opponent. To test the methods under different information gain dynamics, we repeat these simulations at 5 different levels of human rationality. Our results show that, by anticipating information gains along the planning horizon, our method generates efficient plans while remaining safe. For example, in the jaywalking scenario, the certainty equivalent baseline 1 generates overly optimistic plans that are often unsafe since it ignores all but the most likely human intent. On the other hand, the fixed uncertainty baseline 2 brakes conservatively in the face of uncertainty and can only accelerate again once the belief reaches certainty. By contrast, contingency games avoid excessive braking by anticipating future information gain. In the overtaking scenario, we observe a similar pattern. Again, baseline 1 is often overly optimistic, resulting in collisions. Baseline 2 initially incurs a high interaction cost due to the conservative braking maneuver. And contingency games generate more efficient yet safe plans. In our paper, we quantify the performance advantage of our method, showing that contingency games close the gap between certainty-equivalent games and fixed uncertainty games, and that our dynamic branching time heuristic improves the performance of contingency games over a fixed one-step certainty branching time estimate. In summary, we present a model for strategic interactions, allowing a robot to consider a distribution of other agents' intents while anticipating intense certainty in the near future. Please check out our paper for further details and visit the project website for additional material. There, we also provide an interactive demo of contingency games.